Hello everyone, this is Dr. Young, and I'm going to introduce this idea of kinetics to you, right? Which basically asks us, how does reaction occur and how quickly does it occur? Right, so kinetics, like I was just saying, it's the study of reaction rates and mechanisms. For me in our 100 level classes, we're going to focus mostly on this idea of rates and how we can get reactions to happen more quickly, and specifically how that happens in the cell or in a person, right? So like I was saying, it answers the questions of how quickly will a reaction occur and how can we speed up a reaction. Those are the two questions, really, that kinetics answers. So for example, right, if I had this energy diagram, let me just draw our energy diagram right here. Let's say it's an exothermic reaction, it's downhill, we release energy, so we have some sort of reaction. Remember, right, that the difference between the energy level of your starting materials, your reactants, versus your products, right, that gives you your delta H. In this case, it's going to be some negative number because we're downhill, right, it's exothermic. So I'll put exothermic. Exothermic, we know this is favorable because it's downhill, right? All of this is all about thermodynamics. So thermodynamics, right? What happened in terms of the energy that was released or required in order to perform this reaction? That is different from how quickly will the reaction occur. The example that I love to give my students, right, is that the combustion of diamonds is very, very exothermic. It releases a ton of energy, right? So diamonds burning is a very favorable reaction. It's very downhill. It releases lots of energy. However, probably you haven't seen a diamond burning lately, right? I mean, if you've even seen a diamond, I don't exactly see diamonds every day, but, you know, I don't see them, certainly I don't see them on fire. And that's because they have a really large activation energy. And your activation energy is, again, from where you start, but it's to the highest point, right? It's to the highest point of this energy diagram, this hump. And in previous videos, I've mentioned that, oh yeah, there is this hump. Let's not talk about it too much yet. But this is the activation energy. So activation energy. Also abbreviated sometimes as E sub A. And depending on your teacher, if you're not taking my class, my students don't need to worry about this, but sometimes called the delta G double dagger. So the delta G double dagger. So activation energy, right? This is the energy required to overcome that hill to really get the reaction started, right? So kind of back to the rolling a ball down a hill analogy, right? If you had a ball right here, the idea is, yes, it would be more stable down here, and yes, overall, it would release energy, but still, you still have to take that ball and roll it up this part and get the ball up to here before gravity can take over and it rolls down, right? So that's kind of the analogous thing is, how much energy do you have to put into rolling this ball up here in order to get things to really just take off on their own? And so that's the activation energy, and that's what kinetics is all about. Right, so the kinetics in an energy diagram is represented by the size of that hill. You can imagine, right, that if that hill was really, really large, if it was a much bigger hill, for example, it would take more energy to get this reaction going, and it would be harder to get it started, so it would be a slower reaction, versus if it had a smaller hill, it'd be easier to get this reaction to occur, and it would be therefore faster. So we're going to talk about that in these next few slides. Actually, let's take a look at a simulation and take a look at what a reaction that's occurring here and what factors affect it. All right, so I've got the simulator from PhET again, and to kind of orient you here, we've got the reaction, which is an A molecule and then a BC molecule. Those are the reactants, and they're in equilibrium with an AB and a C. And here's the reaction again, and it looks like we have an energy diagram here, so it shows that the reactants are lower in energy than the products. And I've got this high activation energy that I need to get over. And then over here on the right, it's just counting stuff. So how many of the reactants do we have? How many of the products do we have? And I'll put a little bar chart up here too so we can see stuff change over time. So what I'm going to do is I'm going to take a look at how quickly I can get for things to react with one another, right? So first I'm just going to pump in 1A and 1 BC. Boom, just like that. So when I ask myself, is a reaction occurring right now, right? Clearly right now, no reaction's occurring. I just have one of those A's and one of those BC molecules, and they're just floating around in this chamber. Whether this is solution or if this is as gases, either way, they haven't really met. I saw them collide one time, but they still haven't touched, right? So they can't react with one another until they collide, until they've touched. Oh, wait, there was one right there. And maybe we'll get another collision in a second, see if it can react. Oh, nope, it's going to be a little while, right? So one of the issues, right, if you want something to react, they need to bump into each other. They need to collide. And one way to do that, to increase the number of collisions so that you have a faster reaction, is to have more stuff. So I'm going to increase the concentration stuff of everything. So I'm going to add 10 BCs here. Let's add 10 of these BCs, and I'll add 10 of the A's. And if I look at that, right, if I've increased the concentration, so now I have more things in a given area, the question is, do I have more collisions? And absolutely, right, there's lots of things bumping into each other now. Lots of collisions are occurring. But if I take a look, I don't really see an increase in my rate because I don't see any products yet. Nothing's really happened, right? So it's not just that we have to have collisions. We absolutely do need to have collisions, but they need to be one in the right orientation, which means that this A has to smash into the B side of something in order for it to attach to the B side, right? If A smashes into the C side, that's not going to give you a product, right? Because the C is not going to transfer onto A. So the orientation matters. But also, if you take a look at our energy diagram here, right, I have this large activation energy that I need to overcome. And this green bar says total average energy. That's saying that your average particle only has that much energy. Now, there may be some that have more and some that have less, right? This is an average. And in fact, apparently one pair did have enough energy. Look, we've got one finally that did react. Now, we do have an AB molecule and a C molecule. But I'm just sitting here and I'm getting kind of bored. I want more to happen. Or if I'm doing this reaction in the lab, I want to speed this sucker up. And so one way I can do that, right, is to increase the temperature. And let's see what happens when we increase the temperature. One, you'll notice that this bar over here is getting higher and higher, right? The average energy is increasing. So now I have enough energy to overcome that, right? My energy is way up here. I have plenty of energy to overcome that activation energy, that energy barrier. And if I look at my number of collisions over here, right, I have way more collisions. Like they're all moving faster, so I have more collisions per second, so I have more opportunities to react. And so I have more opportunities to react, and they're smashing together with more energy, right? So they have more energy. They're able to overcome that activation energy. And if you take a look at this, right, it's flicking back and forth all the time because we're having more and more reactions, right? Now, because this is an equilibrium, sometimes they go backwards, sometimes they go forwards. But I definitely have more things reacting, or in other words, we've increased the rate, right? So things are happening more quickly. So that's two of the factors that you can play with when you're trying to change the reaction rate, right? One is to increase the amount of stuff, and the other is to change the temperature. So let me go ahead and I'll write that down here. So right, as we just saw here, we saw that when we increased the concentration, right, we caused an increase in the collisions per second, right? Just how many times did things bump into each other? Similarly, when we saw a change in temperature, right, if I increased the temperature, I saw that we had it increased the speed of particles, which allows more collisions per second, so more opportunities to react. Plus, it allowed us to overcome that activation energy, right? If I drew an energy diagram again here, so I had some random energy diagram. Right, this would be my activation energy, my E sub A, my activation energy, and by increasing the temperature, I was allowing my molecules to hit with more force, and they're able to overcome that activation energy. So those are the two things that we saw in that simulator. However, there is a third thing, namely that you can add a catalyst, and a catalyst affects rates by lowering the activation energy. And some other notes about catalysts, right, is that there's something that you add to a reaction. They're not the reactants themselves. Add to a reaction. And they're not the reactants themselves. So add to the reaction. And they are not the reactants. And they are also not heat. Sometimes I hear people talk about temperature being a catalyst, but that's not the case. They're also not heat. They're not temperature. Another thing to note about catalysts is that they're not used up typically or in a reaction, right? So they remain unaffected by a single reaction. So I'll put that they're not used up. Not used up in a reaction. Now, realistically, in the real world, they can degrade over time, but the idea is that you could have like one catalyst molecule or ion or something like that, and it could catalyze tens of thousands of reactions before falling apart.
And so what does it look like when we use a catalyst, right? This energy diagram doesn't change when you use a catalyst. However, it does speed up the reaction. And it does that, like I was saying over there a second ago, is that it does that by lowering this activation energy. It provides a new pathway. So now you have a new activation energy with the catalyst. So new activation energy with the catalyst. Or in other words, right, you have a lower hill to climb, so those reactants can overcome that energy much more quickly, much more easily at lower temperatures. And so it just speeds up the reaction for that reason. It doesn't change the delta G or anything like that, or the delta H. That all stays the same. So this value, right, your delta H, your enthalpy or your overall change in energy remains the same. That doesn't change at all. But the idea is the activation energy does. So let me kind of show you that in another simulator here in a sec.
Okay, so here we have this simulator again, right, where I can change the energy levels of something. And so let me make a reaction that's very exothermic. It's very downhill, but we have an activation energy to overcome, right? And so let me go ahead and I'll add 200 A's here, and I'll start this. So if I'm taking a look at this reaction, right, the idea is that it's very favorable, very exothermic, things really, really want to happen, but you'll notice that it's being very, very slow, right? I've only had 2 A's turn into B's at this point. Only 2, even though it really wants to go downhill, things really want to become more stable. And so what adding a catalyst does, right, we said is a catalyst allows us to overcome this activation energy, right? So for us, the activation energy is this hump right here. Adding a catalyst simply does this. It just lowers the activation energy, and you'll notice that the reaction just sped up like crazy. Now all of those A's are pouring over into that B side. And so it doesn't change the total energy difference, right? I didn't lower or raise the energy level of A or B. I just changed that activation energy. So that's all that a catalyst does. It doesn't like make it so a reaction is favorable or not. It just lowers the activation energy, right? And so now we're seeing, right, the A's are all going over to the B side and the reaction sped up like crazy, right? So again, if you have an activation barrier or an energy barrier, that activation energy, the higher it is, the slower the reaction goes. The lower it is, the faster the reaction goes, right? So to just emphasize that again, let me reset this. So stop, reset. Right, if I have a really high energy barrier and I try to run this, I don't see anything happen. Right, no A's turn to B's. The activation energy is just simply too high. You don't have enough energy to overcome it. So high activation energy, slow reaction. Low activation energy, faster reaction.
So let's sort of summarize how these factors show up in cells, right? So do cells change concentration in order to increase the reaction rates? And the answer is absolutely. Not only is the fact that a cell itself a way to increase the concentration of stuff, but then cells have organelles in them, right? So without a cell, right, try to imagine life without a cell. Then we'd just be a whole bunch of different proteins and molecules trying to react with each other in like a lake or the ocean or something like that. And the chances of 2 reactants meeting each other is going to be really, really low because you have a vast ocean or a vast lake or whatever. And so things would be really, really slow. However, in a cell is a way of concentrating those things in a little area so that they can react faster. If you go a step further, right, even within the cell, you have things like organelles. Organelles concentrate reactants even further. I'll put concentrate reactants. And a good example is, like, for example, say you need to copy DNA or tear it apart for whatever reason, right? And you have like DNA polymerase, which helps polymerize or depolymerize DNA. It's not like that DNA polymerase needs to go searching the entire cell. It's just floating aimlessly in the entire cell, hoping to bump into DNA so it can help react with it. It gets transported into the nucleus where all the DNA is, right? Your DNA is not all over the cell. It's in the nucleus. Also, a good example of that would be, the fact that we concentrate DNA in the nucleus so that the reactions involving DNA can happen more quickly. And that's not the only example, right? We have mitochondria and ribosomes and lysosomes, and all of these different sorts of reactions happen in these specialized parts. And all those specialized parts have higher concentrations of certain reactants and certain catalysts in those areas. So we definitely see that in cells. In fact, that's like one of the main reasons life can exist on the timescales that we imagine is that we have cells and we have organelles to concentrate stuff. So it just makes reactions increase like crazy. Now, temperature is a little trickier one, right? Typically, we don't change temperatures. Typically, no change in temperature. Right, no change. However, of course, we all know that we get fevers, right? We get fevers where our temperature increases, right? So we have an increase in temperature. And there's a few reasons why we get fevers, but one of the reasons is that if we increase the temperature, we increase the rate of our immune system. So immune system, right? Everything is going to speed up. Everything moves a little bit more quickly. The processes that make more white blood cells or more killer cells or whatever is involved in that particular immune response increases so that we can move faster. The other reason why having a fever is advantageous is because all of your metabolic processes are going to speed up when your temperature gets increases, but that also forces a virus's or a bacteria's metabolic processes to speed up also. And sometimes what we can do is we can outcompete those little buggers by making them speed up and burn themselves out while our body is able to overcome whatever infection that we're having, right? Our immune response is able to speed up also, but we have a whole bunch more resources at our disposal than a virus or bacteria does, hopefully. And so we can kind of outcompete them in that way also. The other way that you might see temperature involved in cells or in organisms, right, is the idea of hypothermia or lowering body temperature. So hypothermia, right, you're lowering your body temperature. This is sometimes done on purpose. Sometimes it's induced by a surgeon, right? For example, for like heart surgeries, some heart surgeries or like something on the some surgery on the brain where you have to stop blood flow to the brain. So an example might be heart surgeries. There are ways to like bypass the heart and lungs and stuff. There are machines for that, but sometimes people just lower the body temperature of a patient like crazy so that when they stop their heart so they can work on it, that person doesn't die, right? And the idea is that when they lower the body temperature, you're slowing down all of the reactions that occur in the body, right? Because as you increase the temperature, you increase reaction rates. As you decrease temperature, you decrease reaction rates. And so the reaction rates that we're hoping to decrease are the ones that would kill you if you didn't have a heart pumping and you didn't have lungs that were breathing. So by lowering the body temperature, you can slow down that dying process, all those metabolic processes that are what induce sort of death. Then you also might hear hypothermia. You might have heard about people, surviving being frozen in lakes and stuff like that. Survive freezing water. Let me erase this. There's a woman in Norway, I forget if I think it was like 3 hours that her heart had stopped, which is just insane. But you could survive freezing water, for example. You've probably all heard of some kid falling in a lake or something like that. And then they get pulled out after their heart has stopped for a long, long time and they're able to be revived. Same idea that if you lower the body temperature like crazy, you can slow down those reactions, slow down those processes that would cause you to die. And so that's why, for example, that lady in Norway could survive with her heart having stopped for 3 hours, which is just like insane. It's also why you hear about people, cryogenics and stuff like that. That's a whole other topic. And then the last one, catalyst here, right? Adding a catalyst lowers the activation energy. I put a little note over here, right? The cells absolutely do this. This is why we have enzymes. So enzymes are protein catalysts. Protein catalysts. Some catalysts can be ions. Some of them are molecules. Enzymes is the word for catalysts that specifically are proteins. And there are some like RNA catalysts and stuff like that, but typically they're proteins. And so we'll talk about proteins and catalysts in the next video, talk about how they are affected by temperatures and how specific they are, etc. But that'll be for the next video. So hopefully after this video, you feel a little bit more comfortable about what kinetics are, how we can speed up and slow down reactions, how that relates to the functions of a cell. And that's the main topics that I want you to get. For my class, we're not going to do any like rate laws or anything like that, so you can ignore all that sort of stuff. If you have any questions or comments, you can go ahead and leave them below. Study up and then watch my introductions to enzyme video. Take care.